Hello, hello.
Hello. Okay, this will start streaming soon. Oh, I can hear myself. I think it's working. All right, let's start recording. Hello, everyone, and welcome to the IPFS weekly call. This call where we're able to see the cool stuff that people are doing in the IPFS community. And today we'll get right into it. Ian Preston from Pyrgos is going to tell us about his project, which is UE P2P storage. So we'll learn about how he's using IPFS, and we'll learn more about this really interesting project. So we're just going to get right into it. And Ian Preston, or Dr. Preston, if you can start sharing, that'd be great. Thank you.
All good?
Yes.
Sweet. Good to go?
Okay. Yep. Excellent.
Right, yeah. Is your data secure? Sadly, for most people, the answer is no. So, as Portia just said, I'm going to introduce you to Pyrgos and tell you how we do what we do and why. But first, let's start with some motivation. So, what am I trying to do? What are we trying to do with Pyrgos? I want to store my files online, but without Dropbox being able to read them. I want to be able to share my photos selectively, but without Facebook seeing them. And I want to be able to store my files somewhere, but not in a company that could go bankrupt. And if we dig a little bit deeper, we can split out desires into three main categories. The first one is security. So we want a safe login, and also that means, what does login even mean in a decentralized system? Strong crypto, ideally post-quantum. We want to hide file metadata like names and sizes and directory structures. And we want to be independent of the TLS certificate authorities and DNS. Thankfully, IPFS makes the last two quite easy. The second main category is control. We want to be self-hostable. Again, IPFS solves most of the hard problems there. We want to be able to selectively share files with fine-grained access control. We don't want to expose our contact list to anyone, not even the service provider. By that I mean the storage provider. And we want it to be pseudonymous, so no need to put in a phone number or even an email address. And finally, if we want anyone to actually use it, it has to be convenient. And these days, convenience means a web interface. So you should be able to log in from any device. You should have easy file syncing across devices. You should be able to publish files to people who are not users of the network in an easy way. Essentially, it should be as convenient as Dropbox or Facebook. So let's start with control. The overall architecture we have here, we have IPFS, as we know, is a content address data store. The mapping from hash to data. IPNS, or our equivalent to it, is basically mapping from public key to a hash. We don't use IPNS itself yet, but we'd like to. And the only other thing we have is essentially a PKI, which itself stores its data in IPFS and IPNS. And so a Pyrgos server talks to these three main components. And a Pyrgos client talks to a Pyrgos server. And the only data that's outside of IPFS are these things called follow requests. And that's how we implement the social side of things. And we'll see why they're not in IPFS later. So let's talk about the structure. So the global structure, you have a global file system, and essentially you get space under your username in the global file system. And this is why partially why we ensure unique usernames. So everything has a well-defined path. And your file system has a tree of symmetric keys. We use tweet and ACL. And we have cryptographic links between these keys in a structure called cryptree, which I'll talk more about in a second. And so you end up with a location plus a key is a cryptographic access token or a capability. And that allows you to do something like read a file or read a directory or write a file or write a directory. We explicitly don't use convergent encryption because that leaks the contents of your files. And this is a diagram of the cryptography structure we use. You can see we've got a directory on the left, a subdirectory in the middle, and a file on the right. So each box is a symmetric key, and each arrow is a link from one key to another. And by link, I mean it's the target key encrypted with the source key. So if you have one of these keys, you can follow links from that key around the diagram and derive all the keys. And so, yeah, so you can see a directory has two keys, a base key and a parent key. The base key controls access to the children of that directory. And the parent key gives you access to two things. Well, one thing really is the path. So it encrypts the metadata of that directory, which is its name mostly. And it also has a link to its parent's parent key. So you can follow the backlinks back to figure out the path of whatever you're looking at. Files on the right, we also have two keys, but the files don't have any children. So the base key there is the parent key. And the other key is the data key, which is used to encrypt the actual data. And similarly, the metadata, which has more things now, is like file size and MIME type and so on. They're all encrypted with the parent key. Now this is the tree for controlling read access. So if I wanted to share a file with someone, as well as the location, which we'll talk about later, you share this parent key for the file, the base key. Similarly for a directory, and that gives you access to the entire subtree of that directory with just the one key and location. And the corresponding structure to this for write access looks a lot simpler. So in this diagram, the red boxes are symmetric keys, like in the previous one. The green ones, as you can see, they are key pairs, signing key pairs. So basically, every files and directories look the same from this point, the write cryptography's point of view. So there's just one key for each thing, and that key has a link to or encrypts the key pair for that directory or file. And so if someone has the base write key for a thing, that means that they can then derive the key pair, and that key pair is effectively the IPFS key pair, which is used to sign modifications to that thing. And so that means that they can then modify it. So we've taken the view that write access implies read access. The trees are actually independent, but we only ever share write access with read access. Unix doesn't technically do that, but the exceptions don't really apply to files. They're more for things like a service that's listening, and you can write but you can't read it, kind of thing. So we think that makes sense. So I'm going to talk now about what actually happens when we're uploading the file. So we take the raw file, we split it into 5 megabyte chunks. Each of those 5 meg chunks is independently encrypted, and those are then sharded into 40 fragments. We do a few things within each 5 meg chunk of like rounding it up so that you can't even deduce the size of the file modulo 5 meg. So I can't remember exactly. I think we rounded up to a multiple of at least 4K, maybe more. And then anyway, so during an upload, these encrypted fragments, we put those in IPFS, and then we have an encrypted metadata, the cryptography blob, with Merkle links to these fragment hashes. And each of those cryptography things ends up in another data structure called a champ. So this is an IPLD diagram. So these links are Merkle links. And you can see that you have champ nodes, and then eventually you get to a cryptography node, and that will then point to, if it's a file fragments. And the way we've done it is the serialization, you can't actually, from the network's point of view, you can't figure out if something is a directory or just a small file. So the serialization is identical for both. So that helps you to hide the directory structure, like even just the topology of it, let alone the names. So how does sharing work? So users have a public box-in key, and to send a follow request, what I do is I create a directory for that friend in my space, and then I send a read capability to this directory, and I encrypt it to the friend's public box-in key. And this then gets sent and stored on the friend's storage server until they next log in and retrieve it, and then they delete it after they've processed it. So what this means, so that sharing mechanism, currently that's Curve 25519. So that means shared files are currently vulnerable to a large quantum computer if someone has one. But we'll move to a post-quantum encryption scheme as soon as a clear candidate arrives, which is progressing rapidly. So now the next category, convenience. So what does a login mean in a decentralized system? So we've explained already that PFS is capability based, so we can't stop someone from getting the ciphertext of something. All we can do is control access to keys. And so what we do is we take your password and salt it with your username and send it through a memory hard hashing function called script. And it's tuned to take about a second. And the output of that is three things. We get a root symmetric key, a signing key pair, which is your identity key pair, and a boxing key pair as well. And these are only ever stored in RAM, the private parts, and never written to disk or transmitted. So public links, basically, this is just a capability encoded in the link itself. This is a fairly standard technique these days, but you have the location, which has two parts to it. There's the public writing key, and there's a label in it, which is the lookup key in the champ, and then there's the actual decryption key. And these are all appended after the hash in the URL. And so, as we know, that's not sent to the server. So a public link is actually more like a secret link, because the file is still not actually exposed to the network. And you can share an individual file or indeed an entire folder and its subtree. So now the next category, security. Can a login be cracked? So brute force is practically impossible with a good password. So it's obviously only as secure as your password, and we put some work into trying to help people choose good passwords. So to the point where now we actually have a button which will generate a password for you in the browser. But so with a password that has 14 characters, alphanumeric characters, there's about 2 to the 84 possibilities, or 10 to the 25. So a GPU can calculate about 1 million script hashes per second, measured by Litecoin users. We actually use harder parameters than Litecoin, but it's an estimate. So that means that one GPU cracking a single user's login would take about 10 to the 19 seconds, or 300 billion years. Or if you had 300 million GPUs, it would still take 1,000 years. And those 300 million GPUs, the cost just to buy them, let alone the electricity to run them, would be $300 billion US. So you can compare that to various budgets of various agencies and consider your own threat model. But at the other end of the spectrum, if you drop to even, I think, something like an 8-character password, that actually only costs something like $10,000 to crack in a year. So password length matters. And what about quantum computer-based attacks? So I've already mentioned that shared files are currently vulnerable to a quantum computer. However, files that aren't shared, so just your own files, they are actually already safe. And the reason for this is to get from nothing to reading your files, there's only 2 operations. There's the script hashing, and there's symmetric encryption. and neither of those are vulnerable to a quantum computer. You get like a factor of 2 speed up, and not an exponential speed up. So those are actually fine. And then the classic complaint that JavaScript crypto is insecure. Now, yes, it is, but it depends on your threat model. So if we're targeting the casual user, people who are happy to log into a website from someone they trust, then that's fine. They can just download the JavaScript and log in and do it. For people who are more paranoid and maybe don't trust even DNS, then they can download the source themselves, verify it, compile it, run it locally, and with the power of IPFS, they don't need a DNS address or anything like that. And so, yeah, we can cater to a range of threat models, basically, is the idea. In terms of build security, we have reproducible builds already, both server and front end. We only have 8 JavaScript dependencies, all of them vended. We self-host everything, even fonts. There's nothing from any third party loaded in the web UI. That also helps if you want to run it from localhost offline. We have our own deterministic replacement for Webpack and minifiers. And most of the client code is written in a type-safe language, so Java, and cross-compiled to JavaScript. Demo time, right. Let's see what we can do. Right, can people see this? Hopefully. All right, so here we go. This is the demo server. I'm logged in now as demo. You see we've got a bunch of buttons here. Hopefully they're mostly self-explanatory. This is the social button where we can add friends and sending a follow request and so on. There's a bunch of different files. They've all got thumbnails. The thumbnails are actually encrypted as part of the metadata for the files. So again, server sees nothing. Let's have a look what we could do. So if we go in, we've got some images here. And you can view them in browser or download them if you like. Okay, there's some images. We have a very basic text viewer. So there's a recipe for lamb stew. We can also play videos. This is a more impressive demo. So this is, I'm going to pick a large one. So if we look at the sizes, this Cinta one, that's 120 meg. So if we play that, 120 meg would take something like a minute or so to download. But this will start playing as soon as it's downloaded the first 5 meg. So remember the 5 meg chunking thing? This allows us to start playing, at least in Chrome, not in Firefox, sadly, but in Chrome and Safari iOS, I think it works. We can stream at 5 meg at a time. Buffering something, okay. And at least in Chrome, we should be able to stream and play an arbitrarily large video. It could be a gigabyte big, 10 gigabyte, doesn't matter. Coolio. And I can demonstrate the public link thing. Right, so actually if I go up a directory, not sure why that's so slow, but anyway. So we can create a public link to the media directory, I'll open that in a new tab. You can see there's a bunch of other siblings here to the media directory. And if we go to the public link, you can see the URL there. We can see the things that we've just been granted access to. And if we go down a directory, then all the images are there, wicked. But if we go back up, we can't see any of the siblings. And that's not just a UI thing, that's obviously enforced cryptographically. And everything in there should just work as it does normally. And there's a helpful sign up thing at the bottom. So cool, yeah, the rest of it's fairly self-explanatory. So I'll come back to the talk and slides. Right. So yeah, the other big news is on Friday we launched our alpha for Pyrgos. So if you want, you can sign up. There's a limited number of spots on it. But yeah, alpha.pyrgos.net. If you want to read some more, we have a little booklet, book.pyrgos.org, or just check out our source on GitHub. If future plans, we want to implement messaging a la Signal inside Pyrgos, and an actual document editor, a text editor, and eventually a sandbox, an API for third-party apps to run inside Pyrgos. Yeah, any questions?
Thank you very much. If you have any questions, if you could put them in the chat.
Let me just find the chat.
Maybe stop sharing, that'd be great. Awesome. Do you mind if you, let's see. All right, excellent. First of all, thank you very much for your presentation. That was wonderful. Personally, I really liked your super clear diagrams of how you encrypted the files. I think that was very useful. Thank you very much. And let us start with questions. So we don't have so much time. David, do you mind picking your most pressing question? And then we'll move on to others so they can ask questions.
I'm also fine having my questions answered later. I've been following Pyrgos for a while. Some of these are more like update questions, others are other curiosities. Let's start with Adine, and then Ian can pick one of my questions.
All right, cool, thank you. All right, Adine. Oh wow, you have multiple questions as well. So I'll start with your first one, if you don't mind. The first question is, have you considered using DID-based authentication schemes? How do you evoke a key?
So we take the view, which is kind of a more information theoretic view. Once someone has information, you can't take that information away from them. So to revoke it, so the keys for encryption keys, or they're all symmetric keys, or there's assigning keys, I guess, as well. Basically, you just rotate the keys if you want to revoke access. So you're just re-encrypting the data and re-sharing with anyone who you want to still have access to it with the new keys.
Awesome. Okay, and does anyone else want to ask a question before I get to Adine's second question? All right, second question. How do users share with each other? Does this require external messaging?
So it's all sharing is internal, and so once you can send a follow request to someone, and that then gives them a read capability to a directory in your space for that particular friend. And when you share a file with them, all that does is attach a capability to that file into that directory, which they already have read access to.
All right. Before I go to one of David's questions, I'd like to, Molly, do you have a question?
Well, I actually wanted to pick one of David's questions because I thought it was particularly good about multiple writers. So how do you do kind of collaboration and other things like that in Pyrgos?
So multiple writers are okay. It's whoever has has the key. At the moment, it could be literally the same user on different machines, because our IPNS equivalent is basically it's your storage server, so it's not decentralized in the sense of IPNS. When we move to IPNS, that will be a backup for it in case your machine disappears. But the core thing, I think, for now, is still a centralized service. We don't have fancy CIDTs yet. We would love to do more on those lines in the long term, but for now, this works. And so what that means is that's your centralization point for a given writing space. And so if you try to concurrently modify something, one of them will succeed and the other one will fail.
Okay, so those will be the questions for the live talk. However, this is what we're going to do. If anyone else has any questions, when we put up the video, if you can put up the questions in the comment section, then that'll be another alternative way for you to get your answers. And in terms of next week, our format is going to be slightly different for the IPFS weekly call. Oh, I see Ollie's face of surprise. For the IPFS weekly call, we're going to have lightning talks. So you can sign up 5 minutes during the call if you have a project that you would like to present, or you have something that you're working on that you want to get out there and get some feedback. This would be the perfect forum for that. And that is happening next week, next Monday. Thank you, everyone. And is that a hand, Davi?
Yeah, just a quick question. Is this
Okay.
like a new format, or do we have a pull request to update the call format that is on GitHub? So
There's a pull request on GitHub for the new forum.
Yes.
Oh, there is? Awesome.
Yeah.
Pull
I think we
request,
actually
yes,
merged
then.
it already.
So I think, yeah, that has been merged, and we were about to do it this week, but we are going to do it next week. And it's been something that's been in the works for about a month. So yeah, it's there and it's merged. Cool. All right, everyone. I will see you next week, and have a great week. Thank you, everyone, and thank you, Ian.
Thanks, Ian.
Bye.
No worries.
Tschüss.